is the last lecture in for this class, and I'm going to be talking about, in particular, about direct write technologies. Direct write technologies are a subset of the extrusion-based process, although there are major differences between the extrusion-based processes and the direct write technologies. So we talked a little bit about tissue engineering and the use of additive manufacturing in tissue engineering, and this lecture will mainly focus on direct write technologies. So, and why did direct write technologies come into play? Mainly they came into play as a result of some of the earliest efforts at DARPA related to nanomaterials, because many of these are based on making new types of structures and new types of lines and things like that that you can do uh, with um, uh, very small lines, micro or nano lines that you could never have done with the other types of additive manufacturing processes. As you all know, most of the additive manufacturing processes, when they came into being, they had a resolution of approximately 1 millimeter. In the big scheme of things, 1 millimeter is okay, but when you are trying to create components with uh, resolutions of the order of a few microns, that's not good enough. So what they said is that, what is a technology that has that kind of resolution? The earliest inkjet printing type of technologies. So this set of technologies for direct write are mainly as a result of what people thought we needed in order to get good and very fine resolution microstructures or structures. So when DARPA funded it, it was uh, for making nanostructures or electronic structures. So for example, if you want to create a laser trench in silicon, I mean, if you want to write a line and have as good a resolution as possible, this was the only way that was possible to do that. So this was the earliest technology, and this was called MICE, um, funded by uh, DARPA. So they called it mesoscopic integrated conformal electronics. All these DoD agencies, I mean, I think Scott can appreciate that. We are all so focused on acronyms. So whoever proposed this came up with a very nice acronym, and they called it MICE. So you could write these small lines with the help of the inkjet writing or direct write technologies, and then you can cure it to get the connectivity between different parts of this electronic structure. So this was to enable the manufacture of very complex electronic circuitry within a flexible or complex three-dimensional objects. And there were a number of efforts after MICE. They called it matrix assisted pulsed laser evaporation. They called it MAPLE. Then there was a company, there is still a company called Enscript. They had a 3DE type of effort. They called it 3DE for direct write. Then there is maskless mesoscale materials deposition, or M3D, and now it is called aerosol jet. And of course, I mean, thermal spray techniques, where can it be? I mean, it cannot be too far behind, correct? So that was another set of efforts for getting uh, nice features and very fine features into a structure. So, what is the current status of direct write? You can write or print passive or active electronic components. You can write any kind directly from a computer file without any tooling or mass. And many of these are being used for making insulators, antennas, etc. And it has very, very broad applicability outside the direct write technology. And it is now being used for fabricating structures with very, very tailored thermal, electrical, chemical responses, and maybe biological responses. So if you want to make sensors and things like that, this is a direct write is a very good technology to do that. So direct write has got, I'm sorry, I mean, there are a number of things here. They have 6 broad categories. First one is inkjet based. Next one is laser transfer. Third one is thermal spray, beam deposition, liquid phase, and beam tracing processes. And you are going to be transferring an extremely small quantity of the material automatically and very accurately to create devices on planar or complex geometry. So even on curved surfaces and things like that, you can deposit these materials. Okay, so inkjet based technologies, direct write technologies, are the least expensive and most simple approaches. So many of these technologies have been able to take the inkjet printing approach and modify that to do direct writing. And for that, you need to have many different kinds of ink types. The first one is, of course, the colloidal types of inks, then nanoparticle filled inks. Then the third one is called fugitive. So, you can remove that after you write it. So, you end up with um, a hole or a gap in the structure. The fourth one, the fifth one is called, the fourth one is called polyelectrolyte, and the last one, mainly for ceramics and things like that, is for making, is for sol gel type of structures. You can deposit that. And these inks solidify due to evaporation, gelation, solvent-driven reactions, or thermal energy to leave a deposit of the desired properties. So, and what are the properties that you need for these inks? These inks have to maintain a constant and controllable cross-section, so they should not slump. So which means that when you are depositing them, they should flow very freely, but as soon as they come out of that nozzle, they should become rigid and set up very quickly, so that you can go and put more material on top of that layer, especially if you are going to be building it up layer by layer. So you can either put it as a continuous layer, or you can put it drop by drop. So there are many different mechanisms. There are a couple of different mechanisms to push that ink through an orifice. So you can package them with a scanning system that will first determine the topology of the surface on which to deposit that, and then it goes and deposits that materials. For example, if you have a curvature, it will first determine that and go so that your nozzle can move up and down according to the layer on which it is being deposited. So Nscript has a nozzle design like this because what they have done is In the traditional nozzles, if the standard nozzle were there, so the hole is straight through, so the smaller the nozzle, the higher the pressure you need in order to deliver the material or deliver the ink. But what they have done is they have created a nozzle that is of a different kind. It's a sloping type of a nozzle which allows these materials to actually reduce the pressure that it takes to deposit or dispense this material. So you can dispense these materials even though they have extremely high viscosity. So you can have extremely highly loaded materials deposited onto a substrate. So what is the advantage with having a highly loaded system? So for example, typically solids loading in a binder system or a liquid system is of the order of 30%, because going above that increases the viscosity of these inks by multiple orders of magnitude. So it becomes extremely difficult for these materials to be delivered. But because of this really unique type of nozzle design, it allows these materials to be delivered at extremely high viscosity, because once it is delivered it needs to solidify immediately, and the next thing is that these materials need to be, for example, if they have to be sintered, they should not shrink by a whole lot. So the higher the solids loading, the lesser the shrinkage. So that's the main advantage of this very unique nozzle design. So what are the differentiating factors between the different direct write technologies? The first one is the nozzle design. It directly influences the smallest feature design, and it has a large effect on the types of inks that can be used. The next one is a motion control system. Of course, motion control system is typically, they are very common, and but it allows you to get the high dimensional accuracy and repeatability. And the next one, the final one, is the pump design that allows you how much material you can deliver. And for example, if you deliver it now, after 5 minutes it should deliver the same amount. But if there is a differentiating factor in the viscosity of this material, so how much material you deliver at one stage, at one point in time of that component, will be different from another point of time. So which means that your component accuracy is going to be compromised, and you don't want that to happen. So these are the three factors. Some of the manufacturers are the earliest one. One of the earliest one was Micro Pen. I'm not really sure that they are any longer making machines. And the next one is obviously the Enscript one. So these are the typical sizes and shapes that you want. So for example here, okay, see the repeatability and the resolution. See the higher resolution that you can get with these machines, and compare that with, say, Stratasys or the 3D systems and things like that, where the resolution is of the order of 500 microns. So this is at least 2 orders of magnitude finer resolution, so which means that it is going to give you better components. So, and that's because of the amount of material that you can deliver. You can deliver extremely small volumes of material deposited at any given time. And it can cause the material to be pulled back into the print nozzle at the end of the deposition path. And you can have an extremely large range of viscous materials to be dispensed. So 1 centipoise to 1,000,000 centipoise. So what is 1 centipoise? 1 centipoise is the viscosity of water. What is the viscosity of honey? Maybe like 1000 or 10,000 centipoise. So this is 100 times the viscosity of honey. So when the material is dispensed, after it is dispensed, it is not going to have any kind of shrinkage or slumping. The other off-shelf direct write is first one is Fab at Home, but it's low cost, but it is not very effective for making very fine features and materials. So, but it can be used for making specialized cakes and things like that, but it is not very good for making actual components itself. So what are the advantages of direct write processes? They can deposit very fine line traces. They work with the largest variety of inks, and they can build from low-cost components, and they can be integrated easily into a variety of multi-axis motion control systems. So motion control systems can be made very easily, and they can be retrofitted into a direct write technology. What are some of the disadvantages? The first one is that the material has to be post-processed and thermally post-processed, which means that if you have a polymer in the material, in your direct write ink, it can be compromised. Its properties can be compromised. But it is a useful process. So what are some of the examples? The examples are electronic materials, so you can put metal powders, ceramic powders, thermoset materials, solders, biological materials. So for example, if you have cells and things like that, you can use it to direct write, and you're not going to be applying a whole lot of force on the cells, so the cells are not going to be like, in the case of the extrusion process. We saw that in the last lecture that these materials can get the cells to die. In the direct write, you could probably get away with, you may have cells dying still, but you probably can get a majority of those cells live after the deposition process. Of course, the most common one are the different kinds of nanomaterials. You know that when you add nanomaterials to different kinds of binders and different kinds of carriers, the viscosity is going to go through the roof. So direct write is one technology that can allow you to deposit these materials very easily. You have a variation of this. It is called the quill pen type. So you dip the pen into a container, and then it can put the material down, and the ink is transferred from the pen to the substrate, and it's called so one of these technologies is called dip pen nanolithography technique, and it has been developed by a number of universities, and it is currently sold by a company called Nano Ink. So let me stop here, and I will continue afterwards for the second part of this lecture.